What is powerlifting? Powerlifting is all about strength. Who can lift the most weight? Ironically, even though the sport has the word power in it, power is not the main goal. Power in physics is defined as how fast you can perform work. This is not the case in actual powerlifting because the athlete isn't timed or judged at how fast they can move the weight. Don't confuse this with Olympic lifting, which is a completely different sport. Olympic lifting should actually be called powerlifting because the athlete has to move the weight very fast to get it over their head without hurting themselves. So, how can we relate this to physics? Our body is a machine, and the parts work together to help us complete daily tasks and exercise. These parts are our bones, muscles, joints, central nervous system, etc. Physics concepts like Newton's law, force, work, lever arms, gravity, and center of gravity can all be applied and explained in powerlifting. Since this sport is all about strength, these athletes need to be able to generate a lot of force. They also have a lot of force being applied to them. As Newton's third law would tell us that for every reaction there is an equal and opposite reaction. Force is defined as a push or a pull. The muscles in our body are able to generate internal forces, but muscles can only pull. Even though you can actually push open a door using your muscles, what's actually happening internally is that your muscles are contracting or they're shortening. So, bones, on the other hand, do the push work of force. Bones can compress together during lifts. During the squat, which I'll discuss in a later slide, the spinal column compresses during the lift. This is why it's really important to have proper form. Work is also another very important concept of powerlifting. These athletes need to perform their lifts as efficient as possible so they can do the least amount of work. This will allow them to lift the most weight. Their technique during their lifts dictates the path of the barbell, so ideally in powerlifting, the athletes want to keep the bar in a straight line. By keeping the bar in a straight path, this reduces the displacement. If you wobble the bar, or lean forward or backwards, this creates more displacement for the athlete, so it requires more work done by them to bring it back to the starting position. Our muscles also do a lot of work during lifting, obviously. Since we know that work is a vector quantity, it has to have a magnitude and a direction. The type of work our muscles do is dependent on the direction of the force and the direction of the movement. So you have positive work, which can also be called concentric, and then you have negative work, which is also known as eccentric. The three lifts performed in powerlifting are the deadlift, bench, and the squat. So, the lifter does positive and negative work during each lift, so I'll first explain the positive work done. The first lift is known as the deadlift, which is probably the least technical lift of the three. In this lift, the bar begins from the ground, and the positive work occurs when the bar is lifted straight back to standing position, which is also known as the lockout. The hamstrings shorten, which means they contract, so this is also known as concentric work. These terms of positive and concentric can be used interchangeably. In the bench press, the athlete does positive work and the bar is brought from the bottom of the chest back to the starting position, or the lockout. The pec muscles and triceps contract to push the weight up to starting position. The squat, which is probably the most technical lift, and during this lift, the athlete performs the positive work when he or she comes back to the starting position. When this happens, the quads and the glutes contract, so they are doing positive or concentric work. Now that we have discussed positive work, we can talk about the negative work, which is also known as eccentric. This means that the muscles are lengthening during this time. If you look at the squat, the quads and glute muscles do negative work when the lifter lowers the bar into the actual squatting or sitting position. During the bench press, the pectoralis and tricep muscles lengthen, and they also do negative work during the lowering phase when the bar is coming down to their chest. Lastly, during the deadlift, the hamstrings do negative work when the athlete lowers the bar back to the ground. Since these athletes are moving in the vertical plane, gravity is also acting on them, and gravity is a force. And in powerlifting, we will talk about the lifter's center of gravity specifically. This is the equal distribution of weight and is very important when the lifter has a significant amount of it on their back. An unplanned shift in gravity can cause the lifter to fall and actually fail their lift. In the previous slides, I mentioned how the bar path affects the powerlifter's work, and it also affects their center of gravity. The bar needs to stay typically over their feet to equally distribute their weight. Or you could say that the bar cuts their feet in half. The center of gravity is the center of your base of support, and the base of support is just an imaginary bubble around your feet that you create when you stand. The center of gravity is affected by foot stance and a lifter's height as well. How large the base of support is directly related to that lifter's balance. Widening their stance will enlarge their center of gravity or their base of support and increase their balance. It will also bring them closer to the ground, causing them to decrease their range of motion and their work output. Powerlifter with more mass also has a better balance because they can resist change easier because they have more inertia. This is probably the only case you're going to see in powerlifting where having more mass is more beneficial than just being in shape or having a lot of muscle. A powerlifter doesn't have to have a high inertia to be strong. So mechanical levers, all lifts are levers. In the human body, joints act as pivot points or axes, and the bones are the levers. The varying anthropomorphic measures of bones affect the powerlifter's techniques. While lifters cannot actually change the lengths of their bones, they can alter their technique to better suit their body type. Some people are just a lot more suited for certain lifts. An example of this in lifting is the femur length, which is the big hip, the big muscle of your thigh. The moment arm is the perpendicular distance between the location of force application and the axis, or the joint, in this case. In the photo on the left, you see the person has long femur bones. You can also see how much further they have to bend forward just to reach parallel. In squatting, powerlifters sit at parallel because at this angle, or 90-degree angle, they're able to generate the most torque. The orange line that you see in the photo is the moment arm between the hip joint and the bar, but the barbell is the little circular dot that you see. The person on the left has a higher moment arm of their hip. As the bar becomes further from the hip joint and they lean forward more, the moment arm increases, and this person's squat will look a little bit different than somebody with short femurs. Powerlifters with long femurs will have to work a little bit harder to reach parallel, as it is most advantageous to have short femurs in squatting, which is what the person on the right has. You can see they don't have to bend over as far, and their back angle is a lot steeper. This puts less compression force on their spine. The barbell is much closer to the hip joint in this case as well, and in the next slide you'll be able to see what it looks like in real life and how two different people who are the same height can actually have different bone lengths. So in this photo you can see how femur length can make a squat look different. The girl on the left has shorter femurs, and you can tell this because she's able to sit up fairly well, like she's going to sit in a chair, and her back angle is a lot steeper, as we mentioned in the previous slide. If you look at the female on the right, who is bending over considerably more, you can just tell by looking at her elbows. You can see they almost actually touch her thighs, and the girl on the left, her elbows are nowhere near as close to her thighs as the other girls are. People with long femurs can absolutely still squat, but a good coach will understand physics and apply the knowledge of moment arms to help their athlete lift as much weight as they can based on their anatomy. Next is the bench press, and in this lift it is more advantageous for the lifter to have shorter arms. The person on the left has longer arms, and you can tell he will have a longer range of motion because his elbows will go well beyond that of the person on the right. To alter their technique, if they have long arms, or even just in general, the lifter will arch their back. It also is important to keep the feet planted on the ground when you do this to keep it from altering your balance. The deadlift is actually opposite to the bench press when it comes to arm length. Since the deadlift requires the lifter to lift from the ground, they will need to bend forward. A person with longer arms will have an advantage over somebody with shorter arms, unlike how we just talked about in the bench press. The photo on the slide shows the individual with long arms on the left, will have an advantage because he has a much steeper back angle. The blue line is the moment arm between the hip joint and the barbell. The individual on the right has a higher moment arm because his arms are shorter, so therefore you can tell he's bending over a lot further to actually reach the barbell. In this lift, by applying physics of lever arms, it is definitely more advantageous to have longer arms. So overall, in the previous slide, you can see that some body segment lengths are more beneficial, and powerlifters can't change this, but they can alter their technique. They can also continue to train muscles so they can generate more force, and physics can help explain why some lifts look different than other body types.